Hi everyone, today we're going to do section 6.7, which is graphing rational functions. Again, we did a lot of this yesterday. We're going to do more of it today and get into some slightly more complicated rational functions. And we have a lot of examples, so I'm going to move through each example fairly quickly just to keep the video from being too long. Here we go. So for our warm-up, we have this lovely function 2 over x plus 5 minus 7. If you want to take a minute and pause the video, see if you can find the asymptotes yourself, and then come back to it. But I can tell you that if we do it by translations, we have shifted this graph 5 units. Oops, I always forget to turn on my pen. 5 units to the left. So our vertical asymptote is going to be at x equals negative 5. And then 7 units down, so our horizontal is going to be at y equals negative 7. So for this one, a little bit different. I don't know if you remember from yesterday, we set the denominator equal to 0 to get our vertical asymptote. So we have x equals negative 7/3. And then I mentioned briefly yesterday, and we're going to get deeper into this today, if the degrees are the same, top and bottom, then the horizontal asymptote is really, you just divide the leading coefficients. So it's y equals 1/3. All right, moving right along. So these are just some examples, just so you can kind of see that rational functions can look really different from each other depending on the degree of the top and the degree of the bottom. So for example, we have a simple translated rational function, looks just like the hyperbola that we were talking about yesterday, but here we have a function where the degree on top is higher, and we end up with this kind of slanted look to it. Really unusual. Vertical asymptotes, funky kind of a parabola looking thing in the middle. And then here we have still lower degree on top, but we have an x squared on the bottom, no vertical asymptotes, and just this kind of a little hill thing going on. And then here, lower degree on the top than the bottom, still no vertical asymptotes, but that's not why. But now we have a function that kind of goes woo and crosses over and keeps going. So a lot of different ways that rational functions can look, and we're going to have some fun exploring those today. All right, so in order to really get down to how do we graph a rational function, we've just kind of outlined some notes for you. So the first thing that you need to know, and we've talked about this yesterday, is we've got to be able to find those vertical asymptotes, and we do that by setting the denominator equal to 0. So your domain for almost all rational functions, I can't think of anywhere it's not this, is going to be all reals except your vertical asymptotes. So all reals where x does not equal the vertical asymptotes will always be your domain. Range is a little bit more complicated sometimes. So, and let's talk about horizontal asymptotes. Now, sometimes these are called end behavior asymptotes, which is a great name for them because they are descriptions of what is going on at the ends of the graph, not in the middle. So I can have a graph that flattens out at y equals 2, flattens out, and then the middle goes woo, and then flattens out again. And that's okay. It still has a horizontal asymptote at y equals 2. We're describing what's going on way out here at the ends. What's going on in the middle makes no difference at all for an end behavior asymptote. Only what's going on at the ends. What y value is this end pointing to, and what y value is this end pointing to? For our rational functions, those will always be the same. So later on, we'll get into functions that they're not, but for ours, they'll always be the same. Our horizontal asymptotes that we will deal with in this class and behavior asymptotes will always be horizontal. I'm going to show you how, like, what case gives a slant asymptote, but we're not going to get into how to calculate them. Okay, so here's your test for a horizontal asymptote. What are these n's and m's? They're up here. So if we take a look, n is the degree of the numerator. It's the highest exponent of the numerator. So n is the degree of the numerator, and then m is the degree of the denominator. And if n is lower than m, if the degree on the bottom is greater, then you automatically have a horizontal asymptote at y equals 0. So if the bottom is bigger, horizontal asymptote at y equals 0. If the degrees are the same, you divide the leading coefficients. So your horizontal asymptote, y equals a over c, if the degrees are the same. If the degree of the top is bigger, there is no horizontal asymptote. Now, there will be a slant asymptote, but we are not going to calculate those. Just know that there is no horizontal asymptote if the top degree is bigger. Okay, so for this first one, we have, we're going to start with our vertical asymptote and define it. We're going to set our denominator equal to 0. And so to solve this, I'm going to factor. So I get x plus 4, x minus 2. So x equals negative 4 and positive 2. So we have two vertical asymptotes, one at x equals negative 4 and one at x equals 2. Our domain, you could either write x does not equal negative 4 and x does not equal 2. That would be one way to write the domain. Or you could do what I do, which is negative infinity to negative 4, negative 4 to 2. You should have little unions in here. I should put a union in here. And then 2 to infinity. All right, so I'm going to mark our vertical asymptotes in red. So we have a vertical asymptote 1, 2, 3, 4 at negative 4, and then another one at 2. Pretend that that looks good. All right. Okay, now let's talk end behavior asymptote. Really easy. Since the degree of the top and the degree of the bottom are the same, they are both squared. They're both 2. So degree of the top is 2, degree of the bottom is 2. Then our end behavior asymptote is just the quotient of the leading coefficients. So it is y equals 2. So I'm going to sketch our end behavior asymptote here at y equals 2. All right, x-intercepts. All right, so our x-intercept, we set the numerator equal to 0. You're really setting the whole function equal to 0, but the bottom goes away. So we end up, I'm going to divide everything by 2. So x squared minus 3x minus 4 equals 0. And then when I factor, I get x minus 4, x plus 1. So x equals 4 and negative 1. All right, so I have an x-intercept at 4, 0 and negative 1, 0. So I'm going to plot 1, 2, 3, 4, 0, put a point, and negative 1, 0, and put a point. Now my y-intercept, I set all my x's equal to 0, and I get negative 8 over negative 8, which is 1. So my y-intercept is right here. All right, let's plot a few more points. This side, I don't really need any points. The far sides, the right and left-hand sides, are going to follow the asymptotes. So once you know kind of where any point lies, you can just follow the asymptotes. To get over on in this area, I'm going to plug in x equals 1, negative 1, 2, 3, 4, 5. I'm going to find a y value at x equals negative 5. So if I plug in a negative 5, I get 2 times 25, which is 50, plus 30 minus 8 over 25 minus 10 minus 8. So I get 80 minus 8, which is 72, over 25 minus 18, which is 7. So something around 10, but it's going to be a positive number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Something up here. That's okay. I just needed to know, was it down here or was it up here? It's up here. So I'm going to follow, I'm going to follow my asymptotes on this side. All right. So now I got to figure out the middle. So I know I've got this point and I've got this point. I'm going to need maybe 1 or 2 more points just to make sure that I know what I'm doing. So let's just find out what we've got. Oh, I didn't write this down. 72 sevenths. When x is 1. So if I plug in a 1, I'm going to try and squish some work in here. So I get 2 minus 6 minus 8 over 1 plus 2 minus 8. So 2 minus 14 is negative 12. Over 3 minus 8 is negative 5. I get 12 fifths, which is around 2 and 2 fifths, which is actually above our asymptote. What? Can we cross a horizontal asymptote? Yes, we can. Because a horizontal asymptote is not an electric fence. It's a description of end behavior, and that's all it is. It's just describing what's going on at the ends. All right, I want to plug in x equals negative 2 just for one more point. So I've got 12 fifths, and now I'm going to plug in one more point so I can see what's going on. So at negative 2, 2 times 4 is 8, plus 12 minus 8 over 4 minus 4 minus 8. I end up with 12 over negative 8. So I get negative 3 halves. Negative 3 halves, which is down around here. So I'm going to end up with something that looks kind of like this. Something that looks like that. Kind of an unusual graph. Oh, did I ever write the y-intercept? I don't know if I ever did. It was 1, 0, 1. So my range is actually all real numbers because this middle part of the graph is actually going to hit all real numbers. So I end up with a range of all reals. Kind of an unusual graph. So again, I'm just going to reiterate, you start with your asymptotes. Let the asymptotes help you, especially with the left and right hand sides, and then just plot points for the middle. All right, let's do this one. A little bit simpler. So our vertical asymptote, so we have x squared plus x minus 3. Well, we have an issue because x squared plus x minus 3 does not factor, right? If we were to set this equal to 0, there's no factors that work. If we think about this, there are zeros. We would have to, if we wanted to find them exact, we would have to do quadratic formula. To save time, am going to use my calculator and just find them on my calculator. So if I solve x squared plus x minus 3 equals 0 for x. All right, so I end up with negative 1 plus or minus root 13 over 2, which I'm going to convert to decimals. So I get around 1.3 and negative 2.3. So my vertical asymptotes are around x equals 1.3 and x equals negative 2.3. If you want the exacts, I'll write them down here. They are x equals negative 1 plus or minus the square root of 13 over 2. And you would get that using quadratic formula. But it's really hard to graph that, so we're just going to go with some decimals. So, whoops, okay, converting to red. So we have one that's like this. And we have, negative 2.3. One that's around here. All right. So our domain, you can just write x does not equal 1.3 or negative 2.3. Negative infinity. I really don't want to write out that whole thing, so I'm just going to do it with decimals. Negative 2.3 to 1.3, union 1.3 to infinity. All reals except those two values. End behavior asymptote. We have the greater degree is on the bottom. When the greater degree is on the bottom, you have an automatic end behavior asymptote of y equals 0. So if we plot this, it would be right along the x-axis. We have an end behavior asymptote. X-intercepts, there are none. How are there none? Because if we set the top equal to 0, we get nonsense, right? So there are none, no x-intercepts. It will never touch the x-axis. All right, let me switch here colors. So y-intercept, so if we set all of our x's equal to 0, we get y equals 2 over negative 3. So our y-intercept is at 0, negative 2/3. So our y-intercept is right around there. Okay, so now if we plot points, so I'm going to go ahead and plug in a point just on either side of these asymptotes, just so you know kind of where the graph falls in this region. So let's plug in like x equals 2. So I have 2 over 4 plus 2 is 6 minus 3, so I get 2/3. So 2/2, which means my graph is going to be something like that. All right, and then if I plot a point, let's go to the left side. So -1, -2, -3. So if I check at at x equals -3, I get 2 over 9 minus 3 minus 3, so 2/3 again. So 2/3 somewhere right here. And so I'm going to get a very similar graph on both sides. All right, so in the middle, well, we know we have no x-intercept, so it cannot cross the x-axis. So instead, let's see here. If I plot x equals, oh, whoops, let me write this down. Did I write 2/3? 2/3. If I plot x equals -1, so my y at x equals negative, I haven't been writing my function notation. F of -1 is 2 over 1 minus 1 minus 3. So 2 over -3 or we're getting a lot of 2/3 in here, -2/3. So, which is the same as our y-intercept, which kind of tells me we're going to have something that kind of goes up and down like that. It can't cut through because we know there are no other x-intercepts, so it has to go down this way. And good enough. All right, next, I'm going to pause. So for our next example, so our vertical asymptotes, we said x squared minus 4 equal to 0, x equals plus or minus 2. So graphing those, +2, -2. Our horizontal asymptotes, same degree top and bottom, so you just divide the leading coefficients and you get y equals 2. So we have a horizontal asymptote right there. All right, x-intercepts, set the top equal to 0. So x squared equals 9, x equals plus or minus 3. So we have an x-intercept here and here. And then y-intercept, set all the x's equal to 0, and you get -18 or -4, which is 9/2. I feel like we've done this one. It feels familiar to me. 9/2, so our y-intercept is actually way up here. So 3, 4, right there. All right, so left side and right side always follow the asymptote. Follow the asymptotes, follow the asymptotes. In the middle, that's where you might want to plot a few points just so that you know what's going on. Now, you know it's not going to cross the x-axis. You're not sure if this is the lowest point. If you want to find the y value at 1 and -1, you get -16 over -3 or 16/3, which is what, 5 1/3? 1, 2, 3, 4, third. And then at -1, it's going to be exactly the same. And you end up with this kind of parabola looking thing in the middle. So again, graph your asymptotes. Your left and right far end sides will just follow the asymptotes. As long as you have a point where you know which part you're going to be in, just follow the asymptotes. It's the middle part where you might want to plot a few points just to make sure you've got the right shape. All right, let's just find some horizontal and vertical asymptotes just for fun. So for our vertical asymptotes, set the bottom equal to 0. So I'm going to factor out an x. Factoring is our friend, and we get x equals 0. If 2x minus 5 equals 0 and you solve for x, you get x equals 5 halves. Our end behavior or horizontal asymptotes for this guy, same degree top and bottom. You just divide the leading coefficients. So it's 6/2 or 3. For this one, set the bottom equal to 0. X squared equals 15. So x is plus or minus the square, oops, that minus didn't show up, square root of 15. There's your two vertical asymptotes. Horizontal asymptote, same degree top and bottom. Divide the leading coefficients. 3/1 is 3. What on earth is this? Can you have a graph with a hole in it? Yes, you can. How does this happen? And now we're getting into where we are going to start factoring like crazy. So get ready to factor because we are in the world of factoring. How do we know that there's a hole? Well, let's factor the top. If we factor the top, we get x minus 5 and x plus 2. On the bottom, we have x minus 5. Take a look at what you notice. Normally, when we set the bottom equal to 0, we get a vertical asymptote. But here what happens is this top kind of undoes the bottom. So it kills off the vertical asymptote, but we still have a problem because we're still dividing by 0 at 5. So notice our hole is at 5, and that's where we have common factors. So what happens? Holes occur when you have common factors in both the numerator and the denominator. In the numerator and denominator. Anytime you have the same factor in both the top and the bottom, you're going to end up with a hole. All right, so let's see. How do we generate the equation for a graph? Well, let's take a look at this graph. If the hole wasn't there, I'd be writing y equals 3 and saying have a good day. However, we have a hole at x equals 2. So in order to generate that hole, you need to have the factor x minus 2 on both the top and the bottom. Now, if you were to cancel this factor, what you'd be left with would be this exact graph without the hole, right? So if we cancel this factor, we're back to y equals 3. But if we want the hole, then we need those factors there. So what you do, you put your graph equation like normal, and then you have to add a factor top and bottom for your hole. Since our hole is at x equals 2, we are adding x minus 2 top and bottom. All right, let's try this one. This should be fun. All right, so starting off, I know we have a vertical asymptote at -2 and a vertical asymptote at 1. So I know on the bottom, I want to have an x plus 2, and I want to have an x minus 1, and that takes care, those are my vertical asymptotes. All right, I have an x-intercept at -1. So I know on top I have to have an x plus 1 in order to have an x-intercept at x equals negative 1. So I've got that. We have another problem. Well, we really don't. So we have a horizontal asymptote at 0, which means the degree of the bottom must be greater than the degree of the top, which it is. So our horizontal asymptote, just it checks off. We don't even have to do anything to accommodate the horizontal asymptote. However, do we know that this is the actual equation of this graph? We have to make sure that it's going to pass through this point right here. So if we were to set all of our x's equal to 0, we would want to have a y value of negative 1/2. So let's see, if we set x equal to 0, so I'm going to put y of 0 in here. Then we get 1 over 2 times negative 1, which is negative 1/2, and life is good. If it wasn't, then we would put some sort of a dilation factor in front of our top factor, and we would have to solve for it, which we might have to do in the next one. We'll see. All right, another graph. Sorry, so sorry for yawning. Been doing a lot of videos today. Here we go. So y equals, start with the vertical asymptotes. We have a vertical asymptote at negative 3. So I'm putting an x plus 3. We have a vertical asymptote at 1. So I'm going to put an x minus 1. Let's look at our x-intercepts. We have an x-intercept at negative 2. And we have an x-intercept at positive 3. So I'm putting an x minus 3. All right, so I've got my vertical asymptotes. I have my x-intercepts. Now, I have a horizontal asymptote here, and it looks like it's going right around y equals 1/2. So it's hard to tell exactly, but it looks like it's going right around y equals 1/2. I know I am passing through the point 0, 1, but I want to make sure that I have that y-intercept, or that horizontal asymptote of y equals 1/2. So I'm going to make sure that I have a 1/2 as my leading coefficients, which you can just put on the outside here. It's fine. Okay, so now how do I know that I've got the point 0, 1? So if I put an a up here, let's just see what happens. So y of 0 equals a times 2 times negative 3 over 2 times 3 times negative 1. So we end up with, and we want this to equal 1. All right, so I'm going to cancel. Look at that. Our a is 1. Life is good. So we end up with y equals x plus 2 times x minus 3 over 2 times x plus 3 times x minus 1. Almost done, guys. Couple more examples. All right, equation for this graph. No vertical asymptotes. It's just a parabola, right? So let's see here. We have x equals negative 2, so we're going to do x plus 2. We have an x-intercept at x equals 1, so we're going to have an x minus 1. We think we're done. Oh, let's make sure we do a dilation factor here before I start accommodating for that hole. So I have a y-intercept of negative 2. So if I plug in a 0 for my x's, I get a times 2 times negative 1, and this has to equal negative 2. So we get a equals 1. So I'm down to y equals x plus 2 times x minus 1. And if this hole wasn't here, I'd be good. That would be the equation of my parabola, and life would be happy. But the hole is there. So how do I take care of the hole? Well, the hole is at x equals 2, which means I need to have an x minus 2 over an x minus 2. And now I've got my parabola with a hole at x equals 2. Last thing we're going to do today is just learn how to combine fractions. This is it. Last example of the day. 3 over x minus 2 minus 4. Well, if you remember when you had to combine fractions when you were young, say I had to do, 3 halves plus 4, something similar, right? Well, I would need a common denominator. So I look and I say, okay, I want a 2 on the bottom, so I would multiply this 4, top and bottom by 2. And then I would get 3 over 2 plus 8 over 2, that's an 8, which is 11 over 2, and I'd be done. However, I am not working with numbers anymore. I'm working with letters, but that's okay because it's so similar. So this guy right here, that's still our LCD. So I'm going to multiply this term, top and bottom, by the LCD so that this is also over the LCD. So what do I end up with? I have 3 over x minus 2 minus, now this is the same as 4 over 1. Don't multiply the top and bottom by 4. 4 goes only to the top. So 4 times x minus 2 over x minus 2. Now I can write it all over one LCD. 3 minus 4 times x minus 2 all over x minus 2. And then the only other thing I have to do is kind of clean it up and combine some like terms. So I'm going to distribute the negative 4. So minus 4x plus 8 over x minus 2. And my final answer is 11 minus 4x over x minus 2. All right, that is it. I know it was a big lesson, but